removing nth node from end of the list. Hey everyone, this is Keystrokes. Welcome back to the channel. Today we'll take a look at LeetCode's problem, which is about removing a node from the nth position from the end of a given linked list. This is a medium problem, and this is a very classic interview question. There are so many different ways to solve it. We'll take a look at a simple solution where we iterate the list twice. Then we'll take a look at a solution where we iterate only once. And then we'll do everyone's favorite, which is solving this through recursion. So let's take a look at the problem statement. So we'll be given a linked list, and that basically means giving the head node of the linked list. And then we'll be given an integer n, which would signify the nth node from the end that we'll have to remove. This integer n will signify the position of the node that we need to remove from the end of the linked list. And after removing the node, we need to return back the head node of the linked list. And you must be thinking, what's the point of returning the same head that was provided to us? And that's where this gets tricky, because the head might change if the nth node turns out to be the head itself. So let's take a look at the example. In the first example here, we have a linked list which has 5 elements, 1, 2, 3, 4, and 5. And the value of n is 2. So we need to remove the second node from the end from this linked list, which is the fourth node in this case, as this is the first node from the end and this is the second node from the end. So we remove this node, and then our linked list looks like this, where we have 1, 2, 3, and 5 as a linked list element, and we return 1, which is the head of this linked list. In example 2, the linked list has only one node, which is 1, and n is 1. That means removing this node itself. So in the end, the linked list is basically null. Then in the third example, we have a linked list with 2 elements, 1 and 2, and we are asked to remove the first node from the end. So we remove 2, and we end up with a linked list with only one element, which is 1. And as a follow-up, they ask if we can do this in one pass. So let's see how we can solve this. So let's take a look at all the conceptual knowledge that you need to know before we can dive into the solution. You need to know how to iterate, basically using loops. If you're interested in the recursion solution, then you must know some basics of recursion and how it works. And then you will need to know how to work on linked list, because this question is based on linked list. So let's brainstorm through a simple solution where we'll go through 2 passes. And before we continue, please don't forget to like and subscribe if you have been liking the video so far. Well, let's get into some brainstorming. Okay, so let's say this was our linked list with 5 elements, and A was our head, and we are trying to delete the second node from the end, which will be D in this case. So the first step that we can do is to figure out the length of the linked list. So one way we can solve this problem is to figure out the position of D from the beginning of the linked list. And we can do that by determining the size of the linked list, which will be 5 in this case, and then subtracting the value of n that was given to us. That is the position of D from the end, which will be 2 in this case. This will give us 3. And so the third element from the beginning, if we start from a 0 base index, will be 0, 1, 2, and 3. And so now we know the position of D from the starting of the linked list. In a question, the value of n that we get does not assume 0 base indexing from the end, but I think it just makes more sense to use 0 base indexing in computer science. But if you don't want to use 0 base indexing, all you have to do is to add a +1 to it, and then you can have 1 base indexing. So let's see how we can determine the size of the linked list. We can start by assigning a variable, let's say size as 0, and initialize a pointer that points at A, which is the head node of our linked list. Now we can keep moving this pointer forward until we reach node E, after which this will start to point at null. So at position A, size will be 0, then at position B, then at node B, we can do size +1, which will be 1, and then it will become 2, then 3, and 4, and then 5. So then in the end, we get the size of our linked list, which will be 5. Now, once we know that, we can determine the position of D from the beginning, which will be 5 minus 2, which is size minus n, which will give us 3. And now we should start another pointer, which should go until C. And we want that because we should be updating the next pointer of C, which currently points at D, to now start pointing at E. So we need to go one node behind the node that we need to delete. In this case, it's C, which is at position 2. So we'll run another loop, which will keep going until the position 3 minus 1, which is 2. And once we reach at C, we can do C next to be C next. C next is basically D. So this becomes D next, and D next basically becomes E. So we point C next at E. Now there are some interesting base cases we should talk about. The first one is, what if n points to the head of the linked list? In that case, our size was 5, and size minus n then becomes 5 minus 5, which is 0. And if you have to delete head, we can simply return head.next, which will be B in this case, and that will automatically remove from the linked list. And then B becomes our new head. Okay, so here's the pseudocode for the solution that we just discussed. So we have the inputs as head, which is the input linked list. Then we have a number n, which is the position of the node that we need to remove. So the first thing we'll do is to determine the size of the linked list. And we can do that by running a while loop where we assign current head as the head that was provided to us, and then initialize a variable size as 0. And then we run the loop until current head becomes null. And inside the loop, we keep moving current head to the next node in the linked list. And as we keep moving, we keep incrementing our size. Now, after this loop is done, we know the size of our linked list. That is how many elements our linked list has. Once we know that, we can simply do size minus n, which will give you the position of the node to delete from the start of the linked list. Then we have a simple base condition. If the index of the node that we're deleting is actually 0, then we are trying to delete the head node. So we just return the next node from head. Otherwise, we start a new loop, we initialize our current head to the first node of the linked list, which is the head, and we keep moving forward until we reach the node which is right before the node we need to delete. And we do that by using this condition where we keep moving until we are right before the node that we need to delete. Now once we reach that node, we simply have to skip the node that we're deleting, and we can do that by updating the next pointer of our current head to the next pointer so that we skip the pointer in the middle. And then in the end, we return the head of our linked list. Okay, so let's implement the solution that we just discussed. Okay, so here I have IntelliJ, and I have 3 classes here. We have the solution class, which has the method defined, which LeetCode has, which we can see right here. Then LeetCode also defines this list node class, which is basically how a node in a linked list looks like. And I've treated that right here as list node class. Then we have our main class, where we have some example input that we saw in the question. Okay, so going back to our solution here, let's implement our simple solution. So the first step is to figure out the size of the linked list. And to do that, we create a new list node, and let's name it as current and assign it as head. Then we can create another variable, integer size, which tracks the size of the linked list. Now we can run a loop until current does not become null. And in the loop, we can increment the size by 1 and move our current pointer by 1, which we can do with current.next. Now after this, we get the size of the linked list. Now n is the position of the node to delete from the end of the linked list. So now we can get the position from the beginning, and we can do that by doing size minus n. And let's assign this to a variable, node to delete, which will be from the beginning. Now this node to delete is 0 based. So if the value of node to delete is 0, that means we need to delete our head pointer. And that's our first base case. So if node to delete is 0, that means we need to delete our head pointer, and we can simply return the next pointer after head as our new head of the linked list. So we can do return head.next. Otherwise, we can start a new iteration. So we'll start by doing current as head. And now we run a loop until we reach the node just before the node that we need to delete. And we can do that by this condition where we keep decrementing node to delete by 1, and we keep doing that until node to delete is not equal to 1. So completing this loop by decrementing node to delete by 1 and moving our current by 1. That is moving to the next node. Now once this is done, all we need to do is update our current, which currently points to the node which is right before the node we need to delete, and then update its next pointer to the next pointer, which is next.next. And just to visualize this, let's say if this is our linked list, and if we had to delete node 3, then current would basically be pointing to 2, and current's next will be pointing to 3, and current's next will be pointing to current's next, which is 4. So we update current's next to point to its next, which is basically skipping a node. So when we do that, this 3 basically gets overridden, and then 2 directly points to 4. And once that's done, we just return the head, which is the head of our linked list now. So let's run this program and see if it works on our base cases. Okay, looks like our base case worked fine. Let's copy this and go to LeetCode. So copying this program and going to LeetCode and submitting it right here. So let's run it for the base cases first. And that was accepted. And now let's submit this and see how it performs. Perfect. So LeetCode liked our solution. So the solution we just saw, it required 2 iterations. The first iteration was to figure out the size of the linked list, and then the second iteration was to reach the node that we need to delete. But can we solve this with just 1 iteration? I think we can. And if you have been liking my explanation so far, please don't forget to subscribe and like this video and show me some support by buying some coffee. Also, I just launched my Patreon, and there's only 1 tier in there, which is level 1, which is intended for early supporters. And with that, you get many perks, including some special early supporter perks. You definitely get a shout out on the channel, and you get some exclusive voting power, and you can help me shape this channel. As an early supporter, you can also get on live chats with me, and we can discuss interview questions, or if you need any guidance in general. And also, this will really help me to keep making high quality content for everyone. Okay, so let's get into brainstorming and see how we can solve this just by a single iteration. So let's say if n was 2 and this was a linked list that we have, then we can use a concept of slow and fast pointer. Just try to visualize what that exactly means. So for n equal to 2, it's basically this distance, which is, let's say, a distance of 2. And let's say if we had a pointer which we moved by the same distance from the beginning, then it will stop at b. Now what if we kept moving this 1 step forward every time? So moving this bar forward by 1, then forward again, and then again. So initially it was between these 2, then it became between B and C, then between C and D, and then between D and E. And as this happens, we can tag another pointer, let's say represented by this color, which tracks the beginning of this window, or this duration, or this length. And once the green pointer reaches the end of the linked list, we see that our orange pointer is actually pointing at the node that we have to delete. So that's the basic concept of the slow and fast pointer. So let's see how will that look like. So we start by initializing a fast pointer, which will represent by this green color, and we'll move it by n steps. And n in this case is 2. So it starts at A. So it moves by step 1, which will go to B, and then it will go to C. So this was step 0, where we initialized the fast pointer. Then this was the first step, and this was the second step. And then we initialize another pointer, which will represent by this orangish color, which will be the slow pointer. It's more like a lagging pointer, which will always be behind this green pointer. So we'll initialize this orange pointer or the slow pointer to A again. And now we'll move both the pointers together until the fast pointer reaches the last node. So starting our iteration, we move both of these by 1. So the slow pointer now points at B, and the fast pointer points at D. Doing this again, the slow pointer will point at C, and the fast pointer will point at E. And this is the point where we can stop. So once the fast pointer reaches the last node, we can stop iterating. And now this will ensure that our slow pointer is pointing at the node right before the node that we need to delete. And we need that so that we can delete the node D. If you saw the previous explanation, then this would already make sense to you, but I'll quickly cover it here again. In order to delete node D, we need to update C's next pointer to skip node D and instead start pointing at E. And that's why we want our slow pointer to point at the node right before D, which will be C in this case. So once we have the slow pointer pointing at C, we can simply do slow pointer next equal to slow pointer next. And in this case, if slow pointer is pointing to C, then slow pointer dot next basically evaluates to D. So this whole expression becomes D next, and D next evaluates to E, because E is the next pointer after D. So we update our slow pointer, which is at C, we update its next to point at E, which is what we wanted. And this then just skips over D and removes it from the linked list. Now we should talk about the corner case that we discussed in the first solution. What if n points to the head of the node? In that case, let's see how will the fast pointer look like. So we initialize it at 0, Then we move it 5 steps. So that's step 1, 2, 3, 4, and then 5. And after the 5th step, this is basically pointing to null. And that's the check that we'll add. If the fast pointer, after doing this first iteration of moving by n steps, it makes it to be null, then that means we need to remove our head node. And in that case, all we have to do is to return b as our new head, which will basically remove the previous head from our linked list. Okay, so here's the pseudocode for what we just discussed. Like before, we have head as the input, which is the linked list, and then we have n, which is a number which points to the node to delete from the last. Then we assign 2 pointers, slow pointer and fast pointer, and point both of them to head. Now we start moving fast pointer and we take it n steps ahead. And we do that by running a loop where we keep decrementing n and we run the loop until n is 0. And we keep incrementing our fast pointer, that is moving forward in the linked list one node at a time. Now we have a base case here. If the fast pointer is null, that is, we have reached beyond the end of the linked list, then that means we need to delete the head. And so we just return head.next, as head.next becomes the new head of the linked list. Otherwise, we start moving both pointers, slow pointer and fast pointer, until the fast pointer reaches the last node. And we do that by writing this loop where we keep moving until slow pointer's next is not null. And that's how we know that we have reached the last node. And inside the loop, we just keep updating our slow pointer and fast pointer by moving it node by node. And after doing all of this, slow pointer now points to the node which is just before the node that we have to delete. And so we update the next pointer of our slow pointer to skip the current next node, and we do that by accessing the next node. And so now the next pointer of our slow pointer skips over the node that we need to delete, and the node basically gets excluded from the linked list. And in the end, we just return the head, which is the head of the linked list. Okay, so now let's code the solution out. So let's first define 2 iterators. The first iterator will be the slow pointer, which will point to head for now, and we'll do the same for the fast pointer. So now the next thing we'll do is to move our fast pointer by n steps, and we can do that by running a while loop until n is not equal to 0, and inside the loop we'll decrement n by 1, and we'll move our fast pointer by 1 by using its next pointer. Now we add our base case. If the fast pointer is null, then this basically means that we are trying to delete our head, and in that case we can just return the next node after head, which can be done by head.next. Otherwise, we start another while loop where we'll increment our slow pointer by 1. So we do slow pointer.next, and we do the same with the fast pointer. So we do fast pointer.next as well. And we keep doing this until the fast pointer's next is not equal to null. And this will help us stop the slow pointer at the node right before the node that we need to delete. So the slow pointer is pointing to the node right before the node we are deleting. So all we need to do now is to slow pointer.next and update this next to skip the next node, which we can do by doing next.next, just like we saw in the first solution. And once we skip the node that we're deleting, we can just return the head, which is the head of the linked list. Okay, let's run this again for the base cases and see if this works. It worked in IntelliJ. So now let's copy this and let's go to LeetCode and replace the current solution with the new solution that we just created. And let's run the base cases for this. It worked for the base cases, and now let's submit this. LeetCode really liked our solution. We are faster than 100% of the Java solutions online, and it actually ran in 0 milliseconds, which is blazingly fast. Now here's a small bonus on how to use recursion to solve this problem. So let's see how we can solve this through recursion. Now, if you've seen the previous 2 solutions, our goal is to figure out how we can reach the node which is right before the node that we need to delete. So in this case, if you're trying to delete D, we want to reach this node C so that we can then skip over D and directly change its next pointer to point to E. So we need some mechanism in our recursion to know that what's our current position and if we are at a position right before D. So what if we write a method which returns the position of the node as it backtracks? So let's say for recursion, we start at A, and this bar basically represents the lifetime of the recursion method. And then from A, we call the same method again, but this time with the node B. And then let's say B does the same, calls it for C, C does the same for D, and then D does the same, but for E. and each time we pass head and n as the values. So at E, we can add a base case to check if that's the last node. And we can do that by checking the next pointer. And if that next pointer is null, that means it's the last node. And if it's the last node, it should return its position, which we'll keep as one base index, because n is the position from the end and n has been one base index. So in this case, E is actually the last node. So E can respond back with 1. Now once D gets this value, it can figure out its position by simply adding 1 to it, which becomes 1 plus 1, which is 2. Now similarly, D returns its position that it evaluated, which is 2. So D tells C, my position was 2. Now C calculates its position, which is 2 plus 1, which becomes 3. Now to determine if a node is right behind the node that we need to delete, it just needs to assert that its position is n plus 1 from the end. So in this case, n plus 1 would be 3. So we need to add a condition in a recursion method to detect this. And if a node finds itself in the position that it's right behind the node to be deleted, which is D in this case, then it needs to take some action. So in case of C, that's what's happening. It determines its current position to be 3, which is what we exactly wanted. So once that happens, all C has to do is update its next pointer to point to E, which it can do by simply doing C next equal to C next and then next. And we have discussed this part in the previous 2 solutions as well. So please refer that if this doesn't make sense. So once this is done, now C returns its position, which was 3. Now B determines its position was 3 plus 1, which is 4. Then B gives 4 to A, and then A will determine its position, which will be 4 plus 1, which is 5. And that's how our recursion will basically work. So let's talk about the case if n was actually 5, that is, it pointed to the head node, because in that case, n plus 1 will be 6. And we can see that the recursion stops after 5 here. So there is no 6 that will ever happen. So that's the base case that we'll have to add in our parent method that we'll call this recursion method. So we'll have one method which we'll call our recursion method, which will keep calling itself in a recursion. So our actual method will be calling this with A and N, where A is the head, and this value 5 will be returned to this caller function. So this gets the value 5. So we need to add a base case here, which will check if the returned value 5, that is the position of A, is the same as N, that is we are trying to delete the head. And if that's the case, then all we need to do is return head.next, which will point to this B node. And when we do that, it basically removes A as the head node. So this is the same solution class that we saw before on LeetCode. And let's leave this as it is. Let's copy this and create another function, and let's add util to it towards the end. I just couldn't come up with any better name than this. We'll be calling this util function from inside of our actual function. And let's make this a private function. So this function will basically return an integer, and this integer will point to the node that was processed. So let's add a base case to it first. So if the head.next is null, then this basically means that we are on the first node from the end. So we can return 1 in this case. We are using one base indexing because that's how n works. Then the second base case will be if our current recursion step is at node n plus 1, that is we are pointing at the node which is right before the node that we need to delete, then we should update our head to skip the next node, which we can do by doing head.next.next, which we have been doing all this time in the other 2 solutions as well. And just to make this more clear, so let's say our linked list is A, B, C, and D, and we need to delete C node, which is our nth node. Then our positions basically become D as 1, C as 2, B as 3, and A as 4, and these positions are from the end. And we can see B is actually n plus 1, and that's what we're checking here. If we are at node B, then we need to detect that and skip this node by pointing B's next to its further next. So now let's continue this recursion. So we'll be calling this method itself right after our first base case, and here we'll be passing head.next and n. So thinking of this from the end, when we reach the last node, which is D, the iteration here basically returns 1, and then the return value goes to C. So D basically says 1. Now C's position is 2, and we can find our current position, which let's say we call as current node position, as the value we got from the next iteration plus 1. So if this was returning 1 for the case of D, our current position for C becomes plus 1, which is 2. And then we basically use this in our condition here. If current node position is n plus 1, then we skip the next node and delete it from our linked list. And now because this method is returning the position of the current node from the end, we return the current node position as the value. Okay, so let's call this from our actual method. So calling this method and passing head and n. And this again will give us the current node position, which will be the position of the head node from the end. Now, if n actually pointed to A, that is, if we have to delete the head node, then there is no n plus 1 node because A is the head, and n plus 1 in this case would mean a node before A, which is just not possible. So we have to add a condition in here. If current node position is n, that is, if we are trying to delete the head, then we just return head.next. And that's how we delete the head if we have to. Otherwise, we just return head again. And let's try to run this. And we can see we got our correct answers for the base cases. So copying this again and going to LeetCode and replacing this current function. And let's run it for the base cases that we just saw in IntelliJ. And that was successful. And now let's submit this. And this worked as well. We were again faster than 100% of the Java solutions, and it took 0 milliseconds to run. Well, that's all I had for this video. I hope you liked all the explanation and all the solutions that we discussed today to this problem. This is a very classic question for interviews, so make sure you understand the solution with single iteration, as that forms the basis of so many other questions that you can solve. So if this video helped you, please don't forget to subscribe and like this video, and show me your support by following me on Twitter, buying me some coffee, or following me on so many other platforms. And just a reminder again, I launched my Patreon recently just for the early supporters. So if you like my videos, please don't forget to check it out. The next video will be coming out soon, and so I'll see you then. Thank you so much. Have a great day.